Conservation of energy, and that states that the energy is conserved. So you can't destroy energy and you can't create energy. So with us, we're saying that potential energy and kinetic energy, PE is mgh and kinetic energy is half mv squared. Potential energy is energy due to height. So this object here will have an energy due to its height. It's not moving at the moment, it's just got potential energy due to its height of 10 meters. If this object then falls off that wall, its potential energy will reduce because its height is getting less, but that energy will change form into kinetic energy. And kinetic energy is energy due to its velocity, because we've got a v there. So as this object falls, its potential energy decreases because its height is decreasing, but that difference is made up in its kinetic energy because it's getting faster and faster and faster. So the conservation of energy states that the energy up here is just changed, it changes form into potential energy and kinetic energy. Potential energy decreases because height is decreasing. Kinetic energy increases because the velocity is increasing. Obviously, when it hits the floor, all the energy is dissipated into sound and noise and heat. We don't lose it, it just changes form. So that's the basics of conservation of energy. So we've got an example here of an object 10 meters up and it's 25 kilograms. We've got to calculate the potential energy at 10 meters. So the formula for potential energy is mgh, where m is mass, g is acceleration due to gravity, which is 9.81 meters per second, and height is the height in meters. So in this case, we've got to work out the potential energy at 10 meters off the floor. So at this point here, what is this object's potential energy? 25 kilograms of mass, 10 meters high, and gravity is 9.81. So mgh is potential energy, m times g times h. M is mass, which is 25. Acceleration due to gravity is 9.81, and the height is 10. So it's just 25 times 9.81 times by 10. Gives you 2452.5 joules. So that is the total energy in the system. So up here, the energy up here is 2 and a bit, 0.5. So that there is the energy at the top. We can't destroy energy, I can't create any more energy. So the total energy in the system is 2452. As it falls down, this energy will stay the same. It just gets converted into potential and kinetic. So that is a number we're going to use as the total energy in the system. Next one is calculate PE, potential energy, and KE, kinetic energy, at 5 meters. So now we're saying that what is the PE and KE of that object halfway down. So an easy way of doing it is, it's halfway down, so 2452.5, so if we divide that by 2, we'll get the potential energy, and we'll also get the kinetic energy. But we can do it by formula. So PE is mgh, mass, gravity, height. The mass hasn't changed, neither has gravity, we haven't moved to the moon. and the height now is 5. So we'll do 25 times by 9.81 times by 5 gives me 1226.25 joules. So the total energy in the system is 2452.5. So what we could have done there is divide that by 2, because it's halfway down now. So you'd get the same answer if you did it like this. It's halfway down and divide that by 2. 1226.25. So that is the potential energy halfway down. And now it's moving. Oops, so is my screen. So here it's halfway down, so it's got a PE and a KE. The potential energy there is 1226. And the difference between that number and this number will be the kinetic energy. So the total energy 2452.5. We know PE at 5 meters is that. So the difference is going to be the kinetic energy. So it's the total energy take away PE at 5 meters, which gives you half, really, because we know that. Because halfway down, so half's got to be PE, and the other half has got to be kinetic. 1226.25. So halfway down, they'll be the same. Only halfway down, though. So if you add that and that, so the total energy in the system is going to be the total of the two. Just to check. 2452.5. So we can only do that really when it's halfway down. We divided it by 2. I mean, you can do it when it's a third of the way down or a fifth of the way down. So that's the KE and PE at 5 meters. And the next one is we'll do it when it's 1 meter from the floor. So now it's just about to hit the floor. So it's going to be 1 meter off the floor. This will still be the total energy, but the PE is going to be less because we're only a meter now. We're only a meter off the floor, and it's getting faster, so most of the energy now will be kinetic. So we can work out mgh quite easily. It's 1 meter, mgh, mass is the same, we're still on Earth, and the meter off the floor. So mgh, 25 times by 9.81 times by 1. That's the energy, potential energy, 1 meter off the floor. It's getting less and less and less because my height is getting less and less and less. And the difference between the total energy in the system and the PE down here will be the kinetic energy, because that is the total energy in the system. So that's the total energy in the system, and that's my PE at 1 meter. So the difference will be kinetic. 2452.5 take away 245.25. So 2207.25 is the kinetic energy at 1 meter from the floor. Obviously, it's got more speed or more velocity than height. That's why the kinetic energy is more than the PE. But both of these, you add them together and they should come to the total energy in the system, which is 2452.5. We're assuming there's no losses due to friction, wind resistance, heat, etc., which there would be in reality. 2452.5, 2452.5. So once you've worked out the total energy at the top, that total doesn't change. The only thing it changes is the form of energy. As we lose height, PE comes down, because because the height's getting less. But as it's getting faster, the KE goes up. But PE plus KE has got to equal the total, which in our case is 242.5 joules. Ignoring friction, heat, etc., etc. Next question. Calculate the velocity just before the object hits the floor. So we need to work out just before it hits the floor, what is the velocity? Now, obviously, when it hits the floor, all the energy will be, it'll stop, and all the energy will be converted into noise and force, etc. So I'm going to assume that it's something like a very small amount off the floor, negligible. I'll say 0.1 of a millimeter, which is negligible compared to that. So I'm assuming that all the energy has been converted to kinetic, and as it hits the floor, just before it hits the floor, KE, all of the kinetic energy has been converted into velocity. So the 242.5, the kinetic energy at that point is going to be this. Just very small distance height. Obviously there will be a small PE, but for this case we'll assume all the energy is now converted to KE. So assume at this point, prior to impact, all PE has been converted to KE. So it's a very small amount of height, 0.1 of a millimeter, say. Which means that the kinetic energy prior to impact is going to be 242.5. In reality, it's slightly less than that because we have a very small amount of PE. But for this question, we'll assume KE equals this. We know that KE is a half mv squared, and it's v we're after, so v is velocity, m is mass, half is half, and KE is the kinetic energy, which in this case is this. And this will give us the velocity just before impact, just as it hits the floor. So KE is 242.5. That's the formula. I've rearranged it. I brought the half m down, and then I've square rooted to get rid of the square. So V equals square root of KE over half times m. M is 25 and KE is this. Put that in your formula. In your calculator, do it like this. 2452.5. 0.5 times by 25 is the mass. Press equals gives you a number. Don't want that. 14. So 14 meters per second is the velocity as it hits the floor, or just about as it hits the floor. As soon as it hits the floor, it stopped dead, so all the velocity goes and the energy is converted into other forms. So that is the velocity as it hits the floor, prior to hitting the floor, using that formula there. Obviously, we could use the same formula to work out the velocity at each height if we wanted to, because we know the KE, so we could work out the velocity at each point. And it should be getting faster and faster and faster. Another thing we can do, now we've worked out velocity, is calculate the time taken to fall to 10 meters. So this object is 10 meters high, it's going to fall, and the energy is going to be converted, it's going to gain velocity, and we need to work out what is the time taken for it to fall that distance. So I'm going to use a bit of Suvat. So it starts off, obviously it's not moving when it appears, so its starting velocity u is 0 meters per second. It's going to fall under the effect of gravity, which is 9.81, and just before it hits the floor, v is going to be about 44.3. That's wrong. I don't know where I've got 44.3 from. That's a mistake. So I put that in just to see if you're paying attention. 44.3 is not that. Obviously, it's 14. So 14 meters per second is as it hits the floor. Meters per second. So we know that V equals U plus AT from a previous video. V being final velocity, which is 14, not 44.3. U is initial velocity, which in this case is very handy because it's 0, because it's not moving. A is acceleration due to gravity, which is 9.81, and T is the time which we're trying to find. Rearrange that formula, bring the U across, and divide it by A. V minus U over A is T. So V is 14. That's 14. V is 14. U is 0. Acceleration due to gravity is 9.81. So obviously 14 take away 0 is 0. Divide by 9.81 gives us the time, which is 1.43 seconds. So 1.43 seconds to fall that distance. Don't forget that 14 meters per second is the velocity before impact. This object is not doing 14 meters per second constantly. It's accelerating. So it's doing 14 meters per second prior to impact of the floor. And it does it in 1.43 seconds. So that's using a bit of laws of motion. And the next thing we can do is this object falls, and when it hits the floor there'll be a noise and there'll be vibration and there'll be sound and heat. That's due to the force of impact. We can work that out. So calculate the force the object hits the floor. We know that work done, which is energy, is force times distance. So the work done is the kinetic energy, really. It's the energy that it hits the floor with, which we know is 2452.5. So the total energy it hits the floor with is 2452.5. That was our assumption. And we know it's fallen a distance of 10 meters. It's falling a distance of 10 meters. So we need to work out what is the impact of that. What's the force of impact in newtons? Work done is force times distance. Rearrange that a bit. Bring the distance down, so work done over distance gives us force. We know work done is that number, and 10 is the distance in meters. So that'll give us the force here. So you can either do it by calculator, or you can just move this decimal place that way because we have got a 10 there. Just to make sure, divide that by 10 equals that. 245.25 newtons. So this object hits the floor this way at 245 and a bit newtons. Obviously, every force has an equal but opposite reaction. So the force as well, the floor, will then put an equal but opposite reaction against that object, equal to that. And if the floor can't cope with that, then this object is going to go down a bit. That's why a nail goes into a bit of wood, because the wood can't react against the nail coming in. That is the work done, and the force that this object hits the floor with. We can do another thing. If you could harness that movement and that energy, if you could harness the energy falling, this object falling like they do in hydropower, we can work out the power that could be generated. So we know the power is work done over time, and work done is 2452.5. That's the energy in the system. And it's taken 1.43 seconds to fall, so we can say that the power is work done over time. Work done is 2452.5. The time taking is 1.43 seconds. That divided by that, 2452.5 divided by 1.43 gives me 1715 watts of power, or if you want to do engineering, 1.715 kilowatts. So that's the power that could be generated if you could harness this work done in this force. So that's conservation of energy. Energy doesn't get destroyed, it just gets converted into different forms. In this example, we've used potential energy and kinetic energy. PE is mgh and KE is half mv squared. Assuming there's no loss of friction, there's no energy loss due to heat or anything like that. We've used a bit of SUVAT, V equals U plus AT, and we've worked out the force and the power. So important formula that we need to be aware of: PE is mgh, KE is half mv squared, work done is force times distance, power is work done over time. Make sure you're always in SI units, mass in kilograms, gravity 9.81, height in meters, velocity in meters per second, force in newtons, distance in meters, work done in joules, power in watts, and time in seconds. So hopefully that'll help you with conservation of energy. Like it says, there's a couple of assumptions we make. Hope that helps. Over and out.